Hello and welcome to section 1.2 of our Bridges Probability math class. Today we're going to continue our look into set theory, and we're going to take a look at some set operations, some ways of combining two sets, okay, and maybe more than two sets, but just for now, we'll take it slow and easy, okay. What I would probably do, I think is the best idea to kind of organize this page is go ahead and throw a line down just to the left of the example there, and we'll kind of treat this for the definition and this for the example, so we get a good look at how this thing works, how each one of these works. Sorry. So the union is the combination of the elements of the sets. Okay, and sort of what we think about is that that a number is going to be in the union of the two sets if the number is in either set, or we might say, I might try to write it this way to say that X is an element of, or X belongs to the union of two sets if X belongs to A or X belongs to B. Okay, that's kind of the more formal definition. And this is, technically there's a little bit more to it, but I don't want to get too deep into that. Really, when we're looking at the union, and we do, I kind of glanced over that. Our notation for that is what looks like a U. Okay, it's technically it's called the cup, or the big cup. It doesn't have, this tail on it that a U has. A lot of U's have that tail on it there. It doesn't have that, so don't mistakenly put that. Try your best not to. Okay, so if I'm looking at the union of A and B, then we have set A union set B. It's going to be equal to its own set that is essentially a collection of all the elements that are either in A or B. So it doesn't have to be in order. Of course, I like to put things in order because I'm weird like that. But I see that I have 0 in set B, so we get a 0 in here. I have 1, 2, and 3 in both sets, and that's okay. The only thing I don't want to do is I don't want to break my set rules, and I don't want to put multiple 1s, 2s, and 3s. Okay, so I'm just going to have one copy of the 1, 2, 3. And since 4 is in set A, we're also going to have a 4 in this. Okay, so this is read, the way we read it, is A union B. Yeah, that's what we say when we're trying to say this thing here. Okay, A union B is the set 0, 1, 2, 3, 4. The intersection is still a combination of the two sets, but it's a little more selective. It is the set of elements that are in both A and B. Okay, so again, kind of going along these lines here, I would say that X, some element, is in the intersection, and for that we use the same symbol, just upside down. Okay, so I'm going to say that it's this symbol here. Again, kind of looks like, kind of looks like an N, but it's not an N. Okay, it doesn't have, just like the cup didn't have the tail on the U, this is called the cap. The cap does not have the tail that an N would have. So an element's in A intersect B, or the intersection of A and B, either one, if that element is in A, and instead of or, this is the key word here, we're going to have the word and here. And X is an element of B. So the key word there is and, whereas it was or here. So we include the number if it's in A or B for the union. For the intersection, it has to be in A and B. So it has to be in both of the sets. So A intersect B would be the set of numbers that they have in common. It's going to be 1, 2, and 3, since they both have 1, 2, and 3. Okay. The next one we have is the difference between A and B. And I'll go ahead and get this part out of the way. I seem to always want to put this later. We use subtraction, as we usually do for difference. We use a subtraction symbol. And this would be the set of elements that are in A but not B. Now I am using the idea that we're looking at A minus B as an example. We could look at B minus A, and for that I'd have to flip where I have A and B in that statement also. So it's the set of all objects that are in the first thing, and the idea of minus the second thing means that it's not in the second thing. Okay, it's not in the second collection. So with the example that we have here, we have A minus B, or the difference between A and B. A has, and I'll talk about what it is and talk about kind of an easier way to get there. A has 1, 2, 3, and 4. B has 0, 1, 2, 3. They both have 1, 2, 3. And so I want to take those away. Okay. And really all I'm left with, if I take those away, is 4. So one way that I think about, that's an ugly curly brace, but one thing that I think about is I'm going to go through the elements of A one by one and say, does B have a 1? Yeah, it does. Cross it out. Does B have a 2? Yeah, it does. Cross it out. Does it have a 3? Yeah, it does. Cross it out. Does it have a 4? Nope. Leave it there. Okay, you could literally subtract the numbers off and you would be okay. I thought I had another way to say that, but maybe not. I don't know if we necessarily need it. This is one where, and I don't want to step on any toes because I think it's going to come up a little bit later. This is one where A minus B is different than B minus A. In these two up here, switching them around doesn't change anything. A union B is the same exact thing as B union A, and A intersect B is the same exact thing as B intersect A. But the difference is where we start to see difference. Okay. The last one we're going to talk about is what we call the product or the cross product or the Cartesian product. Okay, we use the old school X for multiplication. And what this does is it creates a set of ordered pairs. And we've talked about ordered pairs before, and it creates a set where we have X's and Y's, where X comes from A, and again, this is the idea of A times B, where X comes from A and Y comes from B. This one's a little bit tougher to do because it's going to lead to so many different ordered pairs in the set. So not only are we taking two collections that probably have single elements, right, a collection of single elements, and we're turning that into ordered pairs as elements. So in this one, it gets rather long. So I do avoid it as much as I can, but it's important that we see that it can be a thing. Okay, I'm going to take every element in A, 1, 2, 3, 4, and pair that up with every element in B, which is 0, 1, 2, 3. So kind of the easiest way I would do that is I would say, I'm going to start with 1 for my first number, and I'm going to go through all of the second numbers. I'm just trying, I know that sets are typically unordered, but the only way I'm going to do this right is if I try to keep it in order. All right, so that's a 1 with every element of B. Now I'm going to move on and start with a 2 with every element of B. Then we have a 3 with every element of B. So 3, 0, 3, 1, 3, 2, 3, 3, and then my 4s. 4, 0, 4, 1. My pen's lagging, that's never good. Keep up. 4, 2, and 4, 3. So it creates this set of ordered pairs that then I can use to create some kind of a lattice system, some kind of a coordinate system. And it's really where the idea of this being called a cross product comes into play. One of your sets gives you one direction of a graph. The other set gives you the other direction of a graph. And so then you have a typically 2x2 coordinate system. Okay, so I want you to do these 4. Go ahead and pause the video and get those done really quick. Hopefully I had a chance to do that, and if you were working on the product, I should have told you, make it a little bit easier. And there's really no way to make it easier other than assuming that you can get it started and somebody can finish it for you. Okay, so let's go ahead and look and see how you did. The union of 1, 2, 3, 4, 5 and 1, 3, 5, 7, 9 would be 1, 2, 3, 4, 5, 7, and 9. It's every number that is included in either of the two sets. The intersection is just the ones that are in both of the sets. So we're looking at 1, 3, and 5. The difference of C minus D, we start with C and we knock off the ones that are in D. Another way you can think of the difference is start with C and get rid of all the numbers that are in the intersection because those are the ones that are also in D. And that makes it a little bit easier. I need to take 1, 3, and 5 out of C and make C only 2 and 4. For the product, like I said, make it a little bit easier on yourself. If you do it all, it's going to be 25 ordered pairs, which would be a little bit daunting to write them all. So I'm going to say it's 1, 1, 1, 3, 1, 5. And then I'm just going to say that continues until you get to your last one, which would be 5, 9. So make that one easier than it is. I'm not too sure why I thought I'd have you do that, because that would be a lot of work. And at some point, my hope is that you just get it, right? That you understand how it's progressing. Okay, so yeah, we kind of answered some of these questions already. Is there a difference between the union? No, they're the same. Anytime you're looking at a union, the order doesn't matter. In the intersections, those are also the same. Okay, it's the differences where we start to see a difference, like I said before. C minus D, we already said was 2, 4. D minus C is going to be, well, 1 doesn't go in it, 3 doesn't go in it, 5 doesn't go in it. D minus C is going to be 7, 9. So they're not going to be the same. There is a difference. Okay. In the products, there's a very subtle difference. And that is kind of my best way to say that is that the coordinates, the X and Y, so to speak, coordinates are switched. So they're definitely not the same, but the difference isn't as drastic as in the difference. Not to overuse that word. Okay, let's move on. Let's see if we can do some of these with our number sets. And I've got another cross product there that would be really ugly. I don't want to fight through that one, so we'll make it a little bit easier. One thing that might help a little bit is to remind ourselves what these actually look like. So the natural numbers are our set of counting numbers. The whole numbers are 0 in the counting numbers. Okay. So when I look at their intersection, when I look at the ones that they have in common, the ones that they have in common are the counting numbers. They both don't have 0, so I can't include 0, but they're all going to include 1, 2, 3, and on forever. So I would say that the intersection of the naturals and the wholes would be the naturals. That would be a little quicker way to write that. Okay. Next one includes the integers, and if we remember what the integers look like, that was where we had no set starting point, but we had some negatives involved. Okay, and if we want to take away the whole numbers are right here. So if I take those away, all I'm left with is -1, -2, and farther negative. And so really what we're looking at is the negative whole numbers, or you could say the negative natural numbers. So z minus w is going to equal, I don't have a fancy way to say this one, but maybe we say -3, -2, and -1. In our next one, we have the rational numbers, the product of the rational numbers and the natural numbers. There is no good way to say this. I can't even really get it started and say, all right, you can repeat the pattern. So I'm going to use set builder notation. It's going to be the set of all x, y ordered pairs such that x comes from the rational numbers and y comes from the natural numbers. Okay. That would be a weird one, being that the rationals are involved, because I mean the trick with the rational numbers is pick any two rational numbers and you can find another one in between. And this is why it's hard to order or to write out the rational numbers. And if you don't believe me, pick any two. Let's say even as easy as 1/2 and 1/4. I can find one in between those. I don't know why I'm making myself work so hard. But what you could always do is you could always find the average of those two, and that would be in the middle. Okay. So if I were to add them, I would get 3/4, and divide by 2 would be 3/8. So 3/8 is in the middle of those two. I could do that again here, and I could do that again here, and that's why the rationals are hard to write out. Not only that, but there's positives, negatives, whole numbers. There's a whole bunch. Okay. Next one, I have the natural numbers union the whole numbers. So I have these two sort of merged together, and it shouldn't take you too much to see that that's just going to end up being the whole numbers. Okay, if I take 1, 2, 3, and so on, and 0, 1, 2, 3, and so on, and I combine those together, I'm going to get the whole numbers. And that actually gives us a kind of interesting idea. If I have two sets that are subsets of each other, because N and W are, N is a subset of W, the naturals are a subset of the wholes, because everything that's in N is also in W plus something else. If I have that, then between these two problems, it kind of tells us a special thing about it. Sorry. It kind of gives us some insight into it. The union of the two coming from this one, if B is bigger than A, and everything that's in A is in B, then the union of the two is always the bigger set, B. The intersection, if everything that's in A is also in B, and A is a smaller set than B, then the intersection is always the smaller set. And that's what happened in these two problems. Okay. Let's look at these last two, and then I'll let you work on your assigned problems on your own. The first one, the intersection of the rationals and the irrationals. So this is saying any number, so this one here is any number that can be written as a fraction, right? Where P and Q are integers. That's what we said last time. And then this set is anything that can't be written as a fraction. So that's anything that can't be written as a fraction. And I want to see where those two overlap. I want to see which ones they have in common. Well, they don't have any in common. And the names kind of give that away. The first one is saying the rational numbers, and the second one is saying the not rational numbers. So when we look for which ones they have in common, they don't have any. And that's an okay answer to say that there aren't any. But how do we say it? That's the trick. That the intersection of Q and I, or the rationals and the irrationals, since they don't have any in common, it's the empty set. And we talked about that last time. The set that has nothing in it. That would be our answer there. Okay? We don't want to say, I know it kind of looks like a zero, and some people might write zeros somewhat that way. We don't want to say it's zero because they don't have zero in common. It's literally nothing. It's like a no solution kind of a situation. But there is a solution. I mean, you can't say that you can't figure it out. That's not what we're saying. We're saying that there isn't anything that they have in common. The last one is more of a definition than anything, but if I take all the rational numbers and all the irrational numbers and put them all in the same set together, that's the set of numbers that we've always dealt with in high school and middle school math classes, the set of real numbers. And that's typically the universal set that we are working under, unless told otherwise. So a couple of things in here that I didn't talk about that's more in the second four than the first four is the idea of complements and how those can factor into figuring things out. And for this one, it gives us a universal set of 1 through 6. So let's at least look at these. A complement, the things that aren't in A. Anytime I have a complement that I'm looking for, we can use that, or we can use another definition that we've talked about to figure out what that is. Anything complement is the universal set minus the A set, minus whatever set you're talking about. It's just anything that's not in that set, but is still in the universal set. And a lot of times, if we're working with the real numbers, that's going to give us a lot of answers and a lot of weird answers, as in irrational numbers and whatever you want to have. Since our universal set is just 1 through 6, the complement of A, since A is 1, 2, 3, 4, is just 5 and 6. Those are the only numbers that don't exist in A but still live in our universe. Okay. So use that, try to figure out those problems, and then there's a couple down here that are important too. Anyways, get those done. If you have any questions, make sure you let me know. Otherwise, have a great day, and we'll see you in class.